We are in Unit 7. This is Notes 1. In this unit, we will deal with area, between curves, under a curve, all about areas. We'll learn about areas, and we cover volumes in this unit as well. So we'll be talking about volumes formed by a curve doing different things. Okay? So this is a fantastic unit. It's an interesting concept. What we can do at the end of this unit is pretty extraordinary. I think it's really interesting, and it's a great application of the integral. So today we take a look at area. Okay, so I'd like to begin just by introducing this to you. I do have a notes packet for you with a lot of examples in it, okay? But each day I will introduce the concept to you so that you understand where these formulas come from, okay? All right, first of all, let's take a look at, I'm going to just make a little graph here. So I'm going to draw, let's draw f of x. I'm going to put f of x up there, and let's put g of x down here somewhere. Okay, so I'm going to call this g of x and this f of x. Okay, and now I need to give this some boundaries. All right, so I'm going to come and give it the boundary from x equals a to x equals b. And our thought is, I would like to find the area bounded by, this is how these will be worded to you, bounded by f of x, the graph of f of x, the graph of g of x, and the lines x equals a and x equals b. So part of the challenge sometimes will be making sure that you're finding the area of what you're supposed to be finding the area of. Okay? So they will tell you what this region is bounded by. I'm going to call this region R. They like to call the region R. So our goal is to find the area of region R here. Okay? All right. So here's the concept. Think about little rectangles. Think about little thin rectangles. Each rectangle has base length delta x, okay? What is the height of each rectangle? How do we get the height of each rectangle? What's that height? Well, that height would be the top curve, which in this case is f of x, minus the bottom curve, which in this case is g of x. So the height would be f of x minus g of x, right? So if we were finding the area of each little rectangle, sometimes the height would be shorter than other times, right? And so the height is changing. That's why the height is a function of x here, okay? All right, so if we found the area of each rectangle, starting with this first rectangle and going to the very last rectangle, okay, we would be needing the height, the base times the height. Base times height, that's the area of a rectangle, right? And base times height would be f of x minus g of x delta x, right? I'm jumping ahead of myself. That would be the area of one rectangle. Right? Well, we want the area of all of the rectangles. We want to add them up, right? What do we do when we add them up? We sum them up. We add them up from the first rectangle to the nth rectangle, however many rectangles there are, and then we what do? We remember last unit, we let the number of rectangles go to infinity, didn't we? When you let the number of rectangles go to infinity and you're adding up areas, that is the integral. That is the integral. So we get the integral from x equals a 2x equals b, right? And it is the height times dx, right? The height times dx. That gives you the area. So when you see an integral of something like this, you're really finding the sum of the area. You're finding the area, right? This is the height and this is the width, the base length, okay? So this would give us the area between the curves. And it makes sense. It just makes sense to do it that way, right? We'll look at some examples in a minute, but before we do, I want to consider another situation. Let's consider another situation. Gosh, what's on the back side of this thing? Oh, that was okay, we don't need that for this unit. Okay, let's consider another situation. You know what, that's going to bother me. Let me get another sheet of paper. I like to use scratch paper for my notes, so I always put it on the back of other pages that we've already done. Anyway, recycle, reuse, and then after I do this side, I do recycle these. Okay, let's look at another situation. What if our function was not a function of x? What if it was a function of y instead? In that case, our curve might look like that. So this might be f of y, okay? And this might be f of g. I'm sorry, g of y. Goodness, one of those days. We all have them. Okay, and we are going to go from, where is my red pen? We are going to go from y equals something to y equals something, okay? You could call this a and b, and that would be fine. Many books like to call this c and d so that they're not confusing. This helps kids remember that it's a y value rather than an x value. Okay, we've been using a and b for x's for quite a while now, and so just to distinguish that, they like to use c and d. No, it doesn't matter though, right? It doesn't matter. So in this case, where are our rectangles going to be? Well, they're going to start like right here, correct? Our rectangles are going to look like this. So what is each base length? What is each tiny, thin little base length? It's no longer a delta x like it was before. Why was this a delta x? Because each little base length was a change in x, right? That was a change in x. That's how we got the dx back here. In this case, each little slice is a delta y. Okay? You guys see that? So we're not going to have a dx this time, we're going to need a dy integral. Each height of the rectangle, what is each height of the rectangle? Okay, each height of the rectangle will be, think about this, what is this distance? What is this distance? Would you say this minus this? Would that be the distance? No, you would go to your larger x value, right? You go to your larger curve minus your smaller curve. That would give you the length. Here's what I mean by that. Let's say that this is 2 and this is 5. What's the length? What is the length? You wouldn't say -3 is the length, right? You would always go to the bigger number and subtract the smaller number. So think of this as the bigger number minus the smaller number. Right minus left. When it's a x graph, you go top minus bottom. When it's a delta y graph, you go right minus left. Okay? So this will be f of y minus g of y. So what is the area? What is the area bounded in here? If this is region R, what is the area of R? Well, the area of R will be the integral from y equals c to y equals d of f of y minus g of y dy. It makes sense. So this would be if your equations, what if we had equations with y's in them instead of x's? well then you would be using this. Okay? All right. Example time. I do love this unit. It makes so much sense. This whole unit is going to make sense to you. Not that they don't always make sense to you. All right, so grab your notes packet because that's where all of these examples are. All right, and in all of these examples, we're going to be finding the area of the region bounded by the equations given in each problem. Okay, now just so that we can do more examples, we're going to use our calculator to integrate. So once we get the integrals, we're not going to integrate by hand. We're going to just use our calculator to do that. It'll just save us some time and we can do more situations because you guys are all really good at integration right now, right? So we don't need to spend all day long doing integrals. We can use our calculators. Okay, example 1. Let us look at, try to figure out what is being, where this region is, okay? We have this curve, and we have this curve, and we have this line and this line. This is also a line, but we have this curve. So sometimes, you guys, I know that you have a calculator in your hand. I know you do, and it might be tempting to go and just graph everything in sight, okay? Know that on the AP exam, though, you may not have a calculator for these problems, okay, for some of these problems. This one you really don't need a calculator for, so this would be a good no calculator problem, okay? And remember, on the AP exam, they might not have you find the area. They might say which integral gives the area, and then you pick out from a multiple choices which integral expression gives the area, right? So some of these, yes, I am going to grab my calculator for, because, and you'll see, it just makes sense too. But some of them, the ones that we can easily do by hand, I would rather do by hand, okay? So this, and plus it's a good review of what these curves look like. This is just a parabola opening up, right? Shifted 2 units up. This is just a line through the origin, right, with slope -1. This is a vertical line at x equals 0, so that is the y-axis. When you see x equals 0, that's the y-axis, right? And then x equals 1 is not too far away. It's a vertical line at x equals 1. So when we sketch this little graph, I really only need to sketch between x equals 0 and x equals 1, don't I? So I'm not going to have much, I'm not going to show much on the negative x side because we just don't need it. So here's x equals 0, so I'm going to draw my x equals 0. Here's x equals 1, so I'll draw x equals 1. Okay, and now I'm going to draw the parabola. The parabola, remember this is an upward parabola, shifted 2 units up. So if I go, I'm not going to, this won't be to scale, but that's okay. If I go 2 units up, that's where my parabola is starting, and then it opens up, doesn't it? When x is 1, where am I at on the parabola? When x is 1? Well, when x is 1, y is 3. So when x is 1, I'm over here at 3. So this is the point 1, 3. Okay? And then this line, and I could make the whole parabola, but I don't need it because I'm already thinking I know what's going to be happening here. The line y equals -x goes through the origin, and it has slope -1, so down 1 over 1. Like I said, this is not to scale, right? So there is that line. So where is the region bounded by those 4 things? Well, the region bounded by those 4 things is right here. Okay, and we want the area of that region. Okay, so the area will be the integral from x equals what to x equals what? From x equals 0 to x equals 1. Why am I using x's? Because my function is all in x's. Okay? And now, what is the height of each rectangle? Think about drawing a little rectangle. What is the height? Well, the height will be the top curve minus the bottom curve. The top curve was the parabola. The bottom curve was the negative x, right? And then what is the length, the base length of each rectangle? Dx. Don't forget your dx, okay? All right, now we get to go stick this in our calculator. So what I want to see on your papers is I want to see your integral, and then I want to see your answer, okay? All right, so let's see. I'm going to go back to my home screen. Remember Math 9, 0 to 1, and then x squared plus 2 plus x dx. And this will give me the area. Okay? From here, round to 3 decimal places. If you would like to change it to a fraction, you can change it to a fraction. Okay? Sometimes that'll work, sometimes it won't work. It depends. If this is a multiple choice question, you may have to change it to a fraction to get the right choice, right? So, but for me, you get to choose. They all mean the same thing. So I'm just going to write it as a decimal, rounded to 3 decimal places. Okay? Not bad. Not bad. Okay, example 2. And it makes sense. So we're finding the area between these curves. Okay, example 2. Here's another parabola, and here's a line. In this one, they don't give us where like the 2 x values to go between, so we're going to have to figure that out from the problem. Okay, so let's graph each of these things. This is just the line y equals x, right? Y equals x. So that is just, you know, through the origin, slope 1. This is a parabola pointing down, shifted 2 units up. So when I graph this, I need to go ahead and graph everything because we don't have the 2 x values to go between. So I'm going to, well, I guess I'll do the easier one first, this up 1 over 1. So there's my line, there's that line. And now for the parabola, I go 2 units up, right? And this parabola is going down. Let's plug in a point. When x is 1, what is y? When x is 1, y is 1. So we've already found our one side of our boundary. We've already found our upper boundary. But the parabola would continue. You can stop it there if you want. The picture, you guys, is just for you. It can be as precise or as sketchy as you like. Okay, it is just for you to visualize. We're drawing the picture for 2 reasons: to see where the area is, and sometimes to find our boundaries. Here we didn't really have to go find our boundaries. Here we have to find our boundaries. Okay, so on the other side, let's plug in another point. When x is -1, we're still up here at 1. What about when x is -2? When x is -2, we'll have 2 minus 4, which is -2. That's also on our line, isn't it? -2 is also on our line. So by sketching the graph, we have found our intersection points. We're going to go from -2 to 1. And I find that happens a lot in these problems. Just plugging in a couple of x values gets you our matching coordinates, our intersection points. If we didn't know the intersection points, how could we find them? We could set the 2 graphs equal, the 2 equations equal, and solve for x, right? That would give us our intersection points. So this would be like that. So we'd have x plus 2, x minus 1, so x would be -2 and 1. And that's exactly what we found out. Okay? So if you don't like to do it this way, you can easily do it that way. It doesn't take too long, right? It doesn't take too long at all. Okay. I can see I got an issue with my camera. Hang on just. This power cord has a little short in it, so I had to jiggle it. Okay. All right. So now we're finding this area. So the area will be, okay, the area will be, you don't have to say area equals. When you give me your integral, I'm going to know what that is, okay? But the area is equal to the integral from the leftmost x. What's your leftmost x? -2. To the rightmost x. What's the rightmost x? 1. Yeah? And now think of your little rectangle. What's the height of your rectangle? The height of your rectangle is the parabola minus the line. So 2 minus x squared minus x. And then the baseline is delta x, so dx. Okay? Calculator time. Okay, math 9 again. -2 to 1. And then 2 minus x squared minus x dx. And we get 4.5. Not bad. I don't think it's bad. Okay, example 3. 2 consecutive intersections of the sine and cosine curves. Okay, well, we know a bit about sine and cosine, don't we? Let's draw them. Let's draw sine and cosine. Sine looks something like this, right? And it keeps going on and on and on and on, right? There's sine. Cosine starts at 1, doesn't it? And its shape is the same. So it does something like that. Okay, and it keeps going, right? So we need the area bound by 2 consecutive intersections of these curves. Well, 2 consecutive intersections, so if this is 1, then the next consecutive one would be this one. So we want that area, the area of bounded by that. So this area right here. Okay? If we saw it a different way, then our integral would look different, but our answer would be the same. And you can see that these should have the same areas, right? Okay, so we need this x value and we need this x value. Okay, so I need those 2 x values because those will be my boundaries. What's the first time sine and cosine have the same value? When is sine x equal to cosine x? Well, this is where I expect you to know a little bit about it. At pi over 4, they are the same, right? Where's the next place they're the same? Well, the next place they're the same is not in the second quadrant, but down in the third quadrant. So what is the pi over 4 angle in the third quadrant? That would be 5 pi over 4. Right? Now, so those are our boundaries. Now we do our rectangle, right? So what's the top of the rectangle? Minus the bottom of the rectangle, that'll give us our height. The height of this little rectangle. Which curve is on top? That was our sine, wasn't it? Which curve is on the bottom? That was our cosine. So sine x minus cosine x, and then the base length is dx. Base times height, that's area. Okay? So that is our integral. We just go to our calculator now. Math 9, pi over 4 to 5 pi over 4 sine x minus cosine x. Do practice putting these in your calculator. It's once you do it a few times, you get very comfortable and accurate at doing it. Even though I still make a mistake every once in a while. It's easy to do. Okay, what if we made a mistake and we put the cosine, we thought, oh, that we made a mistake and we mistakenly thought that was cosine up there. if we did that, what would happen? Let's find out. What if we thought it was cosine x minus sine x? Can area be negative? An integral obviously can be negative. An integral can be negative. Can the area be negative? No. Area can never be negative, okay? So keep that in mind. Keep that in mind. So when you get a negative answer, take a look at how you made your height, because there's a good chance you need to switch the two things. Okay? So I'm going to put 2.828. Does that look familiar to you guys? Anyway, 2.828. Let's take this divided by pi. No, okay. By the square root in there. Okay, that looks familiar though. Okay. Oh, you know what? I think that is 2 square root of 2. Not that you need to know that, but I think that's what it is. Okay, example 4. Here we have this cubic function and this parabola. This is a good one to go and graph on your calculator to see the region. Okay, this is a good one. I'm not going to be plotting points with this guy. This one I could plot points on. This one, no thank you. So let's go to our calculator and see what's happening. Okay, so I'm going to put 3x cubed minus x squared minus 10x up in for y1, and in for y2 I'm putting negative x squared plus 2x. I'm taking a look and making sure I put it in right, because that would be an unfortunate thing to have happen. And I don't have any clue where this is at, so I'm just going to zoom 4. I like zoom 4. So zoom 4. Okay, that was that cubic, and there's the parabola. I think I need to clean this up a little bit. I think I need to see more y values, right? Need to see more y values. So in my window, and my x values, I don't need to see all those x values. I think I only need to go from about a -3 to 3. I think that'll be fine. So I'm going to go -3 to 3. And for my y values, I just need to see more of them, and I don't know how many more, so maybe like -10 to 10, and then I'm just going to turn off my hash marks on my y-axis. Okay, that was much better. I'm glad I went -10 to 10. Oh, look at that. We can see it all now. That actually worked out better than I expected it to. I haven't done these problems since last year, so I did not know that would work out well. Usually I have to play a little bit with that. Okay, so I need to find this x value, don't I? I need to find the area of the region bounded by the two curves. Where is that region now? Well, there are two regions, aren't there? There are two regions. So I need to find this area and add them together. So we're going to have two integrals, right? Not a big deal, just two integrals. Okay, I'm going to find this very leftmost intersection point. So second calc 5 for intersection point, and then I'm going to zoom over there, or trace over there, somewhere there, enter, 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 right? And my first intersection point is when x is -2. So what is that? That's going to be my bottom boundary. That's my leftmost x of this region. Now I need to find the rightmost x of that region. It looks like it's the origin, and if I put 0 in for x, I do get 0. So that is going to be 0. Okay? And for that curve, so think of a rectangle here. What's the height of your rectangle? The height of your rectangle is your top minus your bottom, right? So this is the cubic minus the parabola. So this will be 3x cubed minus x squared minus 10x minus negative x squared plus 2x dx. And that will give us the area of this region. And now we need to add the next area. The leftmost x value will be 0. We need to go find this rightmost x value. So second calc intersection again. I could do this quicker, but that's okay. I'm not in a huge hurry. Enter, enter, enter. So my rightmost intersection point on this region is 2. Okay? And now, think of a rectangle in here. What is the height of the rectangle? The height of the rectangle is the parabola. The parabola minus the cubic, right? So it'll be negative x squared plus 2x minus 3x cubed minus x squared minus 10x dx. Okay? Now this looks like it would be a lot to type in your calculator, right? But fortunately, we have them already stored in to y1 for the cubic and y2 for the parabola, right? So on your home screen, Math 9, -2 to 0 of cubic is y1. What's the quick way to get to y1? Come up here to F4, which is alpha trace. It gets you to F4. Y1 minus y2. And now you don't have to retype it all in. Isn't that lovely? So we got 12. Okay? And now for the next area, and usually I would do it all together. But, and you know what? I'm actually going to go grab that. This is what I would always do. I don't know why I did. I don't know why I separated it, because I always put it on all together. The next area would be Math 9 again. 0 to 2 of, this time it's y2 minus y1, right? So y2 minus y1 dx. So this will give us the sum of the areas. So it looks like each of those areas had the same, each of these regions had the same area. Even though they look different, they had the same area. That's interesting, huh? Okay. Now, for notation's sake, for what to write down for this, I told you I needed to see the integral expression and your answer. Now, if the way they wrote it here, I would have accepted, and this is how I would probably do it, I would have written this as f of x minus g of x dx plus the integral 0 to 2 of g of x minus f of x dx is equal to 24. So if they name these for you, you can use those names in your answer. Okay? Sound good? All right, example 5. Y is equal to plus and minus square root of 3 minus x, and y is equal to x minus 1. Okay? There are 3 curves here. Do you see the 3 curves? Because this plus and minus counts for 2 curves. Let's sketch this out and see what's happening. This is one that you can do on your calculator if you want. You know what? Probably would do this on your calculator. Let's go do this on your calculator. So we're going to have the square root of 3 minus x, and then we're going to have negative square root 3 minus x, or you could say negative y1. Put this down so you can see it. And then we're going to have x, y is equal to x minus 1. That's just a line. Okay, zoom 4. There are the 2 square roots. and here is your line. Okay, I'm just going to sketch this out. Where is that at? 1, 2, 3. So 1, 2, 3. Looks something like that, right? Okay, how are we going to find the area of the region bounded by those three curves? How are we going to find the area bounded by that? I can think of two ways. I hope you can too. We can use delta x this time, or remember that you can always use a delta y, and sometimes it's easier to use a delta y than it is to use a delta x. Why would it be easier in this case? If we used a delta y, then we could do the right curve minus the left curve. And there would only be one integral for that. If we do delta x, on this side of the region, our left boundary is this point. What's our right boundary? Right here. And for that, the rectangle will have height the line minus that negative square root. Over here, what's the height of the rectangle? It's no longer the line minus the negative square root, is it? It's the positive square root minus the negative square root. That would be your height. So if you do it this way, and you can totally do it this way, you will need to make two integrals. And that's okay. You can make two integrals. Not a problem. I'm going to show you how to do this with a delta y though instead. I would like to do this with y's instead of x's and just have one integral. Okay? Regardless, we need to find these intersection points. So second calc 5, enter, enter, enter. Oh no, I don't want that. I know, never mind. It gave me the intersection point of the two square roots, and I don't want that. Come back here. Second calc 5. Okay. I'm coming over here, and I want that. Enter, enter, enter. Make sure, since we have three graphs, we want to make sure we have the right one. So this point is the point -1, -2. Now I'm going to get this point. Okay. So that point, second calc 5, all right, come over here, enter. I don't want to enter on that one, I want to enter on the line, so go down to the next graph, enter, enter. That intersection point is 2, 1. All right. Now, if we are going to use a delta y here, then we're going, here's our rectangle. Here's our little representative rectangle. Okay, so that would be a delta y. Okay, if we're using a delta y, we'll go from the lowest y value to the upper y value. Those will be our boundaries on our integral. The lowest y value is -2. The highest y value is a 1, right? What is, I know I'm going to have a dy for the base length. That's their base. Well, now what is our height? What's our height? Well, the height will be this curve minus this curve. What I need to do, but it needs to all be in y's, right? It needs to all be in y's. So if we need it to all be in y's, I need to take these equations and get them, right now they're y equals, I need to get them x equals. So on this equation, we're going to square both sides. We'll have y squared is equal to 3 minus x. So x is equal to 3 minus y squared. And that gives me just the single y squared curve. And that's on my right-hand side. That's this side. Now I need to subtract this side. Again, I have to make it be x equals, not y equals. This would be x is equal to y plus 1, right? So we subtract y plus 1 dy. if you're doing a delta y, you've got to have y's here, right? No x's. So this is the integral that will give the area. So let's see, math 9, -2 to 1, 3 minus, now our calculator, you guys, our calculator, we could go put y's in to our calculator, but our calculator doesn't care, does it? We could put x's, we could put t's, we could put z's, it can put anything we want in there. As long as this matches your letters in here, it's going to be finding the same number. So I'm going to call this x, even though my x here is representing my y on my paper. Minus x plus 1. Using, if I keep my parentheses, I'm going to make that, keep that a minus. Okay? Dx. So that's 4.5 again. Okay? All right, next up. We've got this curve, y equals 0, that's the x-axis, isn't it? And they gave us some nice boundaries for x, 1 to 3. I love it when they do that. Let's see what we're looking at here. Let's see what we're looking at. So clear out my old stuff, put in my new stuff. Okay, e to the 1 over x all divided by x squared. Whew. Okay, and then I am going to go ahead and put y equals 0 in, because I'm going to need to find an intersection point, right? Maybe. All right, now zoom 4. I think we better see. Now remember, we only care about this from 1 to 3, don't we? We only care about it from 1 to 3. So from 1 to 3, in fact, I could go in here to my x min and x max and make it 1 to 3. Could do that. I think I will do that. There's 1 to 3. So 1 to 3, there's my region, right? So think of a rectangle. What's the height of that rectangle? It's that e to the e curve minus 0, right? Or just the e curve. So the height of this, the area will be the integral of from 1 to 3, right? Of e to the 1 over x squared minus 0. Minus 0, because we're going with the x-axis, right? So you don't have to put minus 0, of course. Dx. So go to your home screen, math 9, 1 to 3 of, and that's just my y1, right? That's it. 1.323. Okay? All right. One last example. Find the value of b such that the area between this curve and the x-axis, that's y equals 0, on 1 to 2, I love it when they give boundaries, is divided into 2 equal areas. We better sketch this and see what's happening. So I'm going to put this into my calculator between 1 and 2 and see what's happening. I'm sorry, not 1 and 2, 0 and 2. So let's do that. Okay, e to the x plus x. Okay, and then still x equals 0, right? Or not x equals 0, still the x-axis, or y equals 0. So I'm going to go for my window between 0 and 2. Well, it kind of went off the screen, so I think I need some more y values, don't you? I didn't need all those negative y values, so I think I can go from -1, but I think I need a higher y value. Maybe 10? I don't know. Maybe 10? Yeah, 10 worked well. Okay. So we have this region. I'm going to sketch it here so that we can draw on it. We have this region in between 0 and 2, right? And in between 0 and 2, this is what our region looks like, right? And it says to find the value of b. You know what? This should say x equals b. Find the value of x equals b such that the area between the area of this region is divided into 2 equal areas. So we want a vertical line, x equals b. We want a vertical line that divides this region into 2 equal areas. Where about will that be, just visually? Well, it certainly wouldn't be over here, and it wouldn't be halfway. It would not be at 1. It would be somewhere to the right of 1. Do you agree? Somewhere here. That would be x equals b. We want to know what is b. Okay? So how can you do this? How can you do this? Well, I can find the area of this piece and set it equal to the area of that piece. That would work. Or I could say, I could write an equation and let that area equal half the entire area. That would work as well. Do you agree? Either one. Either one. I'm going to write them both. So for this side, it would be the integral from 0 to b, right, of, where's our rectangle? Top minus bottom. So e to the x plus x minus 0 dx, and that would equal, right, that would equal this area. And what is that area? Well, the left boundary is b, the right boundary is 2 e to the x plus x dx. That would be one way to do that, and we could work this out and solve it. Not a problem. We could definitely do that. Okay? The other way to do it is, again, to start off with the same thing we started at, integral 0 to b, e to the x plus x dx. But instead of letting it equal this piece, let it equal half of your entire area, right? Half of your entire area, 0 to 2. That would work as well. There's also a third way we could do it, where we take the entire area and set it equal to twice either 0 to b or b to 2. So there's definitely more than one way to do this, all right? Pick one and go with it, all right? I like this when the instructions say just to set up but do not evaluate an integral equation that gives the value of b. I like that way. Okay, but since we actually here have to find b, I think I'm going to come and do this way. Why? Because I have a calculator and I can actually use my calculator on that. I cannot use my calculator on either of these because of the b's in the integral. When I'm putting my integral in, those need to be numbers, right? So I'd like to use this one because it has numbers on one side anyway. I still will have to do some work by myself here, but at least I can use my calculator for that side. So that's what I'm going to do, okay? So I'm going to come and work this side. All right, let's actually integrate. So what's the antiderivative of e to the x? E to the x. What's the antiderivative of x? 1/2 x squared from 0 to b, and that is going to equal what? Well, we can use our calculator for that side. So 0.5, math 9, 0 to 2 of, and there's my y1 in there, dx. So 4.1945280 blah 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 blah. So 4.1945 dot dot dot. Now I will tell you this. What you write on the paper can be rounded. It can be rounded to 3 decimal places. But since this is not our final answer, keep your entire answer here in your calculator. Use this in your calculations. You can write the rounded one here, but use your full decimal in your calculations, because your final answer has to be correct to 3 decimal places. And if you round this and work with that rounded number, your final answer may not be correct to 3 decimal places. So work with it here. I'm going to write the point dot dot, or the dot dot dot, just to let you know I am using that full decimal, not a rounded decimal. But you can just write a rounded one to me, okay? And for AP. All right. Okay, so this will be e to the b plus 1/2 b squared minus, when you put 0 in for x, be careful, because e to the 0 is not 0. E to the 0 is 1, isn't it? So be careful with that. Okay? And now we have to solve this for b, and we can use our calculator to do it. Okay? What I would probably do is, in my calculator, I would bring that 4.1945 over, set the whole thing equal to 0, and then graph it. So I'm going to graph that and find the intersection with the x-axis. Okay, so back to calculator, y equals, I'm going to clear that out. I have the x-axis in here, so that'll take care of that side. So e to the, I want b, but again, I want to call it x here. It's easier to get to, and it's going to graph it, right? Plus 1/2 b squared minus 1 minus, oh, I need that 4 point, I need to use the whole thing, right? Let's come back. Let's store that. I do this a lot. Store that value. That value I'm storing, the little store button down here, stow. Stow that value in for some letter. It doesn't matter what letter, alpha A. In for that letter. That way you can go and use it here. So now I can say minus A. Okay? Graph it, and it needs to be between 0 and 2, doesn't it? So window 0 to 2, that's still good. Let's see what I get. Oh, and I have my weird y values, but I think this will work. Yeah, it'll work. So where does this side equal 0? Right there. I need to find that value, and that value doesn't look right to me. What did I do? What was off, you guys? Something was off. Something was off here. I'm not sure what I did wrong, but I did something wrong here, which really kind of is not good. What did I do wrong? I know it's wrong because I know the answer is going to be somewhere a little over 1. We already talked about how the answer was going to be bigger than 1, and this is going to give me an answer close to 0. So I know that that's not the right answer. So what did I do off here? I'm looking at my work. This is great to see, guys. This is good to see. Hey, it doesn't always work out well, right? Maybe it was what I typed in there. I don't know. Maybe. Let me. Oh, did I not hit enter? I did not hit enter on that. I don't think I hit enter on that, you guys. Now, okay, back here on my home screen, when I went back, I hadn't hit enter. When I said answer stow A, I never hit enter. You have to hit enter for that. Okay, so maybe this will work better. Now that let's graph it again using the different A value. There we go. That's better. Okay. So second calc, intersect 5. Enter, enter, enter. And there is, that makes more sense. We knew it was going to be over 1, right? So x will equal 1.429. Okay? So I'm sorry, b is equal to. B is equal to. All right. Very good. So, great concept today. We talked about area, right? We talked about area between curves. So, time for you guys to go practice.